indeed going to talk about incentives, I'm going to do the for fun part, and then Itay Tsabary will do the for profit part. The for fun part is with my student Michael Merkin, as well as Yan Ji, Arya Klagesmund, Jonathan Peng, and Ari Jules at Cornell and Cornell Tech. So the decentralized cryptocurrencies are going great, as we all know. We see the value plots going exponentially up with some short drops over time. You know this. Oh, sorry. This is Corona incidents in Israel over time. There we go. Yeah, decentralized currencies are going great. And the reason we call them decentralized is that anyone can join, which means that they rely critically on incentives. We need to motivate these new joiners or anyone who can join to follow the rules. And there are three classes of how we can look at this. So initially, starting from Nakamoto, we were looking at altruistic majority. We assume that over 50% of the miners are following the rules, and we asked whether the others can violate the safety guarantees of the protocol. And then the next class is looking at equilibrium. We started asking ourselves what's the best course of action for the players in those systems. So how will a minority miner actually follow the protocol, or is it better off doing something else? This is going on for a few years and still an active area of research. And what we're going to talk about today is the one class up, attacks on the incentive mechanisms, showing what happens when the attacker actually manipulates the incentives of the participants in order to shift them for her advantage. So I'll talk about blockchain denial of service, which is an attack against Nakamoto-like proof of work systems. And then Itay is going to talk about MAD HTLC, about an attack that applies to a very wide variety of smart contracts, real
Did Itay freeze, or is it just me? Okay. Okay, I'm sure he'll be back in a second. This actually happened to me like a couple of weeks ago. My laptop crashed mid-talk.
Sorry.
Awesome.
Am I back?
There you are.
You're back.
Perfect. So I'm not sure where you lost me, but this is the center of the talk. I'll talk about blockchain denial of service. Importantly, this is a sabotage attack. This is not about making a profit. This is about someone willing to make an effort, expend resources in order to damage the blockchain. So this is from a few months back, but still the top 10 cryptocurrencies by market capitalization, about 80% of these run proof of work Nakamoto blockchain, and the attack applies to all of them. And there are a lot of good or evil reasons to run a denial of service attack against a blockchain. This could be a competition from a state or from another cryptocurrency, as well as short selling, which is an revenue source. You're trying to make money not on that chain itself. And still, these the major cryptocurrencies didn't experience denial of service or anything like it. Why is that? Because they're very expensive or ineffective. So here's a 51% attack against the blockchain. You have the end of the blockchain and you have a majority of the miners are evil. Then honest miners generate the block and the attackers just ignore it and they generate empty blocks along the chain. The honest parties are going to switch to the longest chain because that's the rules. and so on and so forth. So we get an empty chain and we have a denial of service attack. But that's incredibly expensive. You have to have, the attacker has to have as much or rent as much mining power as the rest of the system. The other option is attacking individual node with an eclipse attack. You prevent access from a node to the rest of the cryptocurrency network, and you can manipulate them, but this really only affects a single node and does not have a significant effect on the rest of the system. So what we're going to look at the model as follows. We'll have n miners, and given the chain, they can either mine on the longest full chain or stop and do nothing. This is sometimes called petty compliant, and Carlston and company did it, the famous Princeton paper. We're also, so the miners basically follow the rules, but they may deviate a little bit as long as it's not interrupted. They can also do SPV mining, which means they extend the longest chain that only has headers. This is technically possible, and the attack is still going to work even if they're able to do that, and we'll see why it's important in a second. The model, the system will progress in rounds. In every round, there's a block added. The scheduler chooses the miner to add a block according to the mining power of that miner. This is standard. And then note that we'll only have expenses for mining when the attack is, when the miner is actually working. If the miner chooses to stop and not mine, then she doesn't bear any expenses. And it's easy to see that because of the memorylessness property of proof of work mining, there is no action chain between blocks. So the decision point is when a block is generated, each miner decides what they want to do until the next block. Now, what are the miners, the rational miners, trying to achieve? Their utility is the revenue, what they're making minus the cost per second, expected as t goes to infinity. So when mining, the cost per second is going to be some constant c, and when not mining, both the cost and the revenue per second are going to be 0. When mining, the revenue is going to depend on the behavior of the miner and the other miners. Now, we're also going to look at this important property, which is called the mining profitability. This is simply the ratio between the revenue and the costs of mining. And we're going to assume that if the attack is not taking place, then this omega b is larger than 1, meaning the miner is making more than they're spending. Otherwise, we don't need to attack. They would stop by themselves. The attacker, and again, this is not a profit, the attacker is to stop the chain. So she doesn't care about on-chain revenue. This is going to stop anyway. She's going to commit to a strategy. She says, this is the strategy I'm going to take, and she's going to stick with it. And she has some rushing level, denoted gamma. This is about her ability to control the network. I won't go into more details here. So the attack proceeds as follows. The attacker tries to motivate miners to stop mining by she's ahead. So once she's able to generate a block, she'll publish only the header of the block. And the miners now have two options. They can either ignore it, extend the block, or stop mining and do nothing. And like I said, they can also SPV mine, extend just on the header. So if they mine, they just ignore intentionally the knowledge that they have that can improve their states, or they don't see it, and they generate a block. The attacker at this point publishes the rest of the block, and there's a race. The attacker might win, or the honest party might win. If the attacker wins, the honest party is sad. She's making less than she was supposed to. Another option is SPV mine. If the rational miner chooses to SPV mine, the attacker is never going to publish the content of the block. Eventually, everybody will give up on this branch, and they will extend a different chain. Again, the rational miner is sad. This is not a good option for her. Finally, she can stop mining, go rest, lose nothing, win nothing, and wait until something happens. So the analysis is done with a Markov chain. We do a Markov chain per strategy, and we compare the utilities of the different Markov chain and ask ourselves, when is stop mining an equilibrium that is the best course of action for everyone from the perspective of the rational miner when the attack is taking place. This is a parameterized chain, so the parameters depend on the choices of the other miners. This is what it basically looks like. There is only one difference between the different strategies, which is the action when the attack is active. I'm not going to go into the details, but give you the bottom line instead. So the attack, we get a closed form expression that bounds the cases where the attack is going to succeed. So basically what we see is that if the base profitability is small enough, it's easy to tip the scale and make mining not profitable. If the miners are small enough, so smaller miners are easier to manipulate. And if the attacker is large enough, they're going to activate the attack more frequently and win more races when they occur. Also, if they have better control of the network, of course. Now, we plugged in these expressions into real data we collected from different public sources, showing us the profitability when we take the best mining hardware. We took the parameters and the cost of electricity, etc. And we see that most of the time, this is the good news that is going to turn bad. But most of the time, the attack is very expensive. It's much more expensive than a 51% attack. However, it is enough for the attack to be effective only at a small period of time. So if for a short period of time even, the profitability drops for whatever reason, the attacker can issue the attack then and convince everyone to stop mining. These graphs are for Bitcoin, and you see that since the halving, the situation has become not so great. And circled there is an important and surprising for us point, which is that if there are some altruistic miners in the system, then they're actually going to make things easier for the attacker. So the altruistic miners strengthen the incentives of rational miners to stop mining. The attacker is going to have an easier time stopping the rational miners. So this was the blockchain denial of service. The attacker incentivizes miners to stop by showing she has an advantage. It's considerably cheaper than a 51% some of the time. And the conditions vary with the attacker size, the miner size, the network control, as I showed. It's getting worse over time because the mining industry is getting more mature, so the profit margins become smaller. The downside is that I don't have good news on the side of mitigations. This is an open question. It is important to notice that this attack specifically does not affect Ethereum because of the uncle reward. So this is good news for Ethereum.
Itay's audio went out again.
Sorry, yeah, I hope we're stable now.
You're back.
So I said that the attack is not effective against Ethereum because of uncle rewards. And it's another open question of whether there is a similar attack effective against Ethereum. So this is to show you how incentive manipulation can affect the security of the system. We can make an attack much cheaper. And this was about proof of work Nakamoto-like blockchains. And I will now, we will now switch gears and let Itay take the screen and talk about something completely different, much more smart contracts in general on any underlying chain. Thank you.
Thanks. I need you to stop sharing so I can start sharing.
I like your background, by the way, the Game of Thrones theme.
Oh, thank you. Do you see my slides? Great. Yeah. So hi, everybody. My name is Ittay Tsabary. I'm a PhD candidate at the Technion. And I'll present today our recent paper called Mad HTLC, because HTLC is crazy cheap to attack. It's a joint work with Matan and Itay, who just spoke. The short version is this. There is this super useful contract called HTLC. It's pretty much everywhere. And sadly, it's vulnerable to minor incentive manipulations. That means that the users of the contract can manipulate miners into helping them attacking the contract itself. The attack is much cheaper and affects way more systems than what we previously thought. But the good news are that we present a solution in the form of another contract, which we call MAD HTLC, which actually uses the miners to enforce its correct execution. So I'll go through the background quickly, and then we'll get into the details. So we all know blockchain, cryptocurrencies. What I want to emphasize is that they facilitate transactions of internal tokens, and that the correct execution relies on incentives. Okay, the system incentivizes miners to get the system to work. The main data structure is a blockchain, just a chain of blocks. The last block determines the system state. Blocks look as follows. They have some metadata in them and a list of transactions. Transactions have to be valid, and if the transactions are invalid, then the block is invalid, and we just disregard these blocks. The entities or principles that create the blocks are miners. They're rational, they're incentivized by the protocol to do so, and they get to pick what transactions they include in blocks. Transactions move the internal tokens around, and tokens are actually stored in what we call contracts. Now, I'm going to use the UTXO lingo, but this is the same in account-based systems like Ethereum and Libra and so forth. So these contracts hold the tokens, and to move the tokens or to transact the tokens, you have to provide some input to the contract to make it evaluate positively. That means there's some sort of code that you have to put inputs into, and the code then says either success or failure, and only success means you can move them on. Now, it's important to note that two transactions might conflict. So they both are valid independently, but they just conflict with each other because they span the same contract, and what we call is just they double span the same contract. Transactions are relayed through the peer-to-peer network, and they do not affect the system until they're put in a block. And importantly, they offer fees to the miner. Specifically, the miner that puts a transaction in the block gets the offered fees. So moving to something a bit different about higher level constructions, I'm referring to systems that are built atop of the blockchain. Namely off-chain payment channels like Lightning in Bitcoin or OMG in Ethereum. I'm not going to get into the details of what that is. Same for cross-chain atomic swaps, something that is built on top of blockchains. The thing I want to emphasize, though, is that both of these and many more other systems all use a contract called HTLC. You can see it on the left here in the red boxes, and to the right in the blue ones. They use this contract, the HTLC contract, and this is basically the building stone of that. And all these systems, they do a good job at incentivizing their users, in my example, Ant-Man and Batman, to behave honestly. Okay? So what's that HTLC, or in its full name, hash time lock contract? So HTLC uses three contract primitives. These are primitives that the predicate of the contract uses. The first is pretty much straightforward. A digital signature. A user has to sign using his private key to create a signature. The second is a hash lock. That means the user, to make the contract evaluate positively, has to reveal some hash preimage. This is a cryptographic hash function. Sorry, there was some background noise. It has to reveal a hash preimage. And the third is a time lock, which means that the user has to wait for the timeout to elapse. So the timeout starts when the contract is created, basically when the transaction creating the contract is put on the blockchain, and you can't move the money until some timeout elapses. So how does the HTLC uses these three primitives? In the following manner. So user Ant-Man can move the money using his digital signature, and by solving the hash lock, that means providing relevant hash preimage. Alternatively, Batman can redeem the contract, again with his digital signature, and by waiting the time lock to expire. Okay, so there are two ways to redeem this contract: either Ant-Man with the hash lock or Batman with the time lock. So this figure illustrates in which blocks which of these transactions can be inserted. So assume the HTLC was initialized in block X. That means admin's transaction can be in any of the following blocks. However, Batman's transaction has to wait for the timeout to elapse. So that means it can only be inserted in block X plus T and so forth. And I also want to remind you that these two transactions double spend because they both span the same contract, the HTLC, and that the miners, they're the ones that pick what transaction goes into which block. Okay? So we have this correct execution premise about HTLCs that states that if Ant-Man creates a transaction before the timeout, then that transaction is included in the blockchain. And a key observation is that this completely fails to take into account miner incentives, right? The miners are the one that pick what transactions get into which block. So how can we just assume that? And yeah. So going back to these systems, the off-chain payment channels and the atomic swaps, these are only correct under this premise that the HTLC works as intended. And when we make premises that don't necessarily hold, we open ourselves to attacks, which is exactly what the HTLC attack does. So it's as simple as that. But Batman can just bribe the miners to exclude Ant-Man's transaction until the timeout elapses and get the transaction inserted instead. And the profit of that would be just the tokens of the HTLC minus what he paid in bribe. That what remains is a clean profit for him, right? If he hadn't done anything, then he wouldn't get anything anyway. So why not? And in this scenario, Ant-Man is obviously sad. He lost his money. Batman is malicious. He attacked the system. And the miners are somewhat happy because they get paid more. They got more to do the same thing, right? They just had to pick a transaction. It doesn't matter for them which transaction. And if Batman offered more, then why not? So previous work actually discussed that. I'm referring to Windsor et al. It was published last year in Euro S&P workshop. And they suggested using elaborated smart contracts for this attack. This attack requires coordination, right? Batman has to offer a bribe, and the miners have to notice that, and they have to coordinate and act together to make it work. And they suggested a few smart contracts that can achieve that. And these contracts are, they're only, you can only create these on Ethereum. You can't do that on Bitcoin, right? They use opcodes that you can't, you don't have in Bitcoin. And additionally, these require prior deployment. Batman has to set up the attack. He has to create the bribing smart contract, and he has to put some funds in it. So that has some additional costs, and he has to pay them regardless if he succeeds or not, right? He actually paid to create a contract on the blockchain. They also have an analysis of the attack cost, how much bribe would Batman need to pay, and it's with respect to the timeout T. And they have two bounds, a lower bound that says, right, it's constant, the timeout doesn't matter. And they have an upper exponential bound that says, right, if the timeout is T, you have to pay 2 to the T. And that suggests that maybe the attack is not that bad because we can just increase the timeout, right? So maybe it's not as usable as we would have wanted, but we mitigate the attacks. So enters HTLC's crazy chip to attack, our work. We show that you don't actually need these elaborate smart contracts. You can simply use the transaction fee mechanism the bribe can be as simple as a transaction that pays a higher fee. That means this attack applies to all systems, not just the ones that offer more elaborate contracts. It doesn't require prior deployment, but we can just create a transaction with the fee. It has no cost if the attack fails, right? You would have gotten nothing anyway, so no additional costs. And also, the attack cost is actually lower. We show that their upper bound is actually the lower bound, okay? So that means that increasing the timeout, it's irrelevant, it doesn't help. I'm gonna walk you through the analysis. So we analyze this as a game where the players are Ant-Man and Batman, and this is something new, the miners as well, okay? We call that the HTLC premise neglected miners. We do not do that. We consider them as participants in the game. The strategies are, for Ant-Man and Batman, are their respective transaction fees, how much fee they offer with their transactions. And for miners, is what transactions they include in the following fee blocks. The utilities are the tokens at the game conclusion. And we analyze this as a progressing game. So there are rounds that represent the creation of blocks. So the first, they create the first block, and then they create the second block, and so forth. Some game theory. This is probably, some of you are familiar. I'm going to go through this really quick. So the best response of player P, this is a definition, given the way that all the other players act, what strategy gives them the highest utility? Nash equilibrium says that given a vector of strategies, like fix the way all players act, are they all playing their best response strategies? That suggests some sort of a steady state. Everybody's happy with the way they act. And we also use this, well, I want to mention this refinement of Nash equilibrium called subgame perfect equilibrium, which means that every subgame is also Nash equilibrium. So basically that means that all players are happy at any stage throughout the game. They can't increase their utility by deviating throughout any of the game. So you can consider this as the axis represents the creation of blocks, and you have this original subgame representing all the suffixes of the creation of the next T blocks, and then someone created a block, so we move to this subgame, and so forth. And throughout each of these, subgame perfect equilibrium means that everybody is happy with the way they chose to act. So SP has a nice property. You can analyze it using backward induction. This is the game of tic-tac-toe. Sorry, how's it called in English? Tic-tac-toe? I'm not sure. Anyways, so one player puts X's, the other one puts circles, and the way to analyze it is consider you're in this state, and now you want to decide what you want to do. So the player plays in his head for both sides, saying, okay, I'm gonna put the X in this spot, and then the other guy's gonna retaliate. I'm gonna put the circle here, and so forth. And then basically what happens is you look at all possible game conclusions, and you derive backwards what's the best action for you to take, so that the game transitions to the best outcome on your end. So this is backward induction, and this is what we use to analyze the game. The results of this analysis show the following. First, the required fee depends on Ant-Man's transaction fee, the average transaction fee in the network, because when the miners don't include Ant-Man's transaction, they get to include other transactions, which offer them some reward instead. Also, it depends on the miner resource distribution, meaning how much hash rate each miner has. But it's not affected by the timeout, okay? That's what I started with. Increasing the timeout doesn't help. It doesn't make the attack more expensive. So you can't simply solve it by doing that. We also ran some numbers and analyzed Bitcoin. We analyzed this attack using Bitcoin's current conditions. And it's actually very, very cheap. So we actually found instances on Bitcoin that when you spend $20 for the attack as bribes, you could have gotten $26,000. So that's like Ittay mentioned, Abraham mentioned buying Bitcoins in 2016. So yeah, that's in the same scale, or even better. So what we get is HTLC is just crazy cheap to attack. I also should probably mention that the current prevalent Bitcoin implementation, which is called Bitcoin Core, rejects future transactions. That means that when Batman introduces the Zai paying fee transaction, which can only be included in T blocks, the default behavior is to just ignore that transaction. And the way they set it is because it's a DOS prevention mechanism, okay? You just don't want to get the network dirty with future transactions. But that's not a consensus rule, okay? Any node can implement whatever it wants. It's not part of the Bitcoin protocol, just some local optimization by the client. So taking into account that these transactions, these future transactions actually benefit the miners, they have incentive to do that, right? These open up profit opportunities, so why not? And to show this is actually quite easy to implement, we just removed that, that optimization from Bitcoin Core. So it took us only 150 lines of code. It was quite simple to implement. So if miners have an incentive to do that, there is no technical difficulty, or it's not a constraint. Okay, so after I've hopefully convinced you that everything is broken and bad and everything is collapsing, I'm going to show you a solution, which we call MAD HTLC. Recall that the problem was that HTLC neglected the miners, just didn't account for their incentives. So what we decided to do in MAD is exactly avoid that problem. We're going to use the miners and we're going to incentivize them to enforce the correct execution. What does MAD stand for? It actually stands for the Mutual Assured Destruction, which basically means that if one party attacks the other, they both end up losing. It's a deterrence mechanism that's supposed to incentivize the parties not to attack each other. So in our case, if Batman attacks, both Lee and Antman loses. Here's from Pirates of the Caribbean. They're all trying to shoot each other, but they refrain from doing so, because if they will, then their friend will shoot themselves. Yeah, you got it. So how does MAD HTLC look like? It actually comprises two contracts. The first is the deposit contract. It's basically serves as the HTLC. This is the main functionality. And we also have an additional contract, which we call the collateral. It's just an auxiliary contract. Both of them are initialized together. That means in the same block, they share some parameters. The deposit just holds the HTLC token. So if you wanted to have an HTLC with 5 tokens, you'd put these 5 tokens into a deposit contract. Excuse me. And the collateral holds only a few additional tokens. So it's not an addition, it's not a significant overhead. Okay? Just a few tokens, roughly the same amount as the average transaction fee. And together, they achieve the desired behavior. How does the deposit contract look like? So recall HTLC had 2 options. Now we have 3 in the deposit. And also notice that we use 2 different hash locks. So the first option says that Antman can get the tokens by solving the first hash lock 1. Or Batman can solve this is pretty much like the original HTLC. Option 2 says that Batman can get the tokens by waiting out the time lock and by solving an additional new hash lock, which we denote as hash lock 2. Or alternatively, anyone can get the tokens by solving the 2 hash locks. Okay, so hash lock 1 is the same as Antman's, hash lock 2 is the same as Batman's, and anyone that can solve both of them can get the tokens without any time lock or something like that. And when I say anyone, I actually refer to any miner, because what happens is that when Antman and Batman, both of them decide to attack each other, or one of them attacks the other, they both publish the pre-images for the two hash locks, which enables miners just to create a transaction redeeming the contract themselves. So if I'm a miner and I see both of these transactions, I just create a transaction of my own and take the money myself. The collateral uses the same parameters and says that Batman can get the tokens of the collateral contract after the timeout. This is also pretty much like the original HTLC. Or alternatively, a miner can get the tokens of the collateral contract by solving the two hash locks and by waiting out the timeout. So let's see what we get when we combine these two together. So first scenario, only Ant-Man tries redeeming the deposit. Recall this is this option. So if only Ant-Man tries redeeming the deposit, he publishes the answer to hashlock 1. Batman does not try to redeem the deposit, so it doesn't publish the answer for, or the preimage for hashlock 2. So we get that only one of these is revealed, so miners can't redeem the contract themselves. And what we get is that Ant-Man gets the deposit and Batman gets the collateral. Second scenario, Batman tries redeeming the deposit. So Ant-Man does not publish hashlock 1. Batman does publish hashlock 2. Miners, again, can't redeem the contract themselves because only one of these is revealed. So we get that Batman gets tokens of both of these. Third scenario, both of them try redeeming the deposit. This is the attack scenario. Both of the hashes are revealed, the pre-images are revealed. So any miner can just take the token himself. We get that MAD HTLC is incentive compatible. That means that all participants, and namely Ant-Man and Batman, are incentivized to act in the way we want them to. And it also allows us to remove the miner altruism premise. We don't have to assume that miners are altruistically going to let the Ant-Man's transaction in just because we assume them to do so. And I want to state again that if Batman attacks, both he and Ant-Man loses. So this is the mutual assured destruction point. We implemented that contract in Bitcoin. So by that contract, I mean the deposit and the collateral. The deposit has only a slight overhead of 30 bytes. That's a few cents to deploy, a few additional cents to deploy. And I should also mention that for the off-chain use case, the HTLC or the MAD HTLC most of the time doesn't even end up on the blockchain. This is only like a failsafe for unilateral closes. And only on disputes it ends up on that chain. And in that case, maybe you'd want the more secure one. Anyways, we also ran this mainnet experiment. We actually created MAD HTLC on the blockchain and redeemed it using all the various redeem paths. Here to the right, you can see the transaction that created the contract and the 3 transactions that redeemed it. Well, sorry, this transaction created 3 instances of the contract, and then we redeemed each of them using a different redeem. I'll also mention that this scheme requires miners to be rational, or it counts on miners being rational. Specifically with respect to which transactions they choose to include in blocks. And currently, or in current Bitcoin Core, that doesn't really happen. It has like this really standard, straightforward behavior, and it does not allow more elaborate considerations. So we actually patched that again, or had another patch of Bitcoin Core, where we actually exported all the TX optimizations to a Python module. The reasoning is that Python is easier, it's simpler, and you can just customize it as you please. And we customized it to support the rationality with respect to MAD HTLC. Obviously, you can just plug in any rational considerations you'd like. So to conclude, HTLC is vulnerable, attacks are cheap, and the time, just naively increasing the time lock does not help. it affects all systems, not just the Ethereum likes. The reason for the attack is it fails to account for miner incentives. We have mad HTLC that solves this problem. It considers all participants' incentives and uses miners as part of the design. It is incentive compatible and has a miner overhead. And we also made some Bitcoin Core patches. So we have the paper available on archive. And thank you for listening.
Good job. I have one question. It's mostly me I want to make sure I understand the attack. So is the issue that we're doing a HTLC, Alice, Bob, the Caroline. 1 second, let me just mute my Slack because it's not going to shut up. So Alice is sending coins to Bob and Bob's sending coins to Caroline. Now,
you're referring to an off-chain payment channel.
Yeah, exactly. HTLC payment. So now the route has completed and we're going backwards. Bob wants to get the coins from Alice, but Alice isn't cooperating. So Bob is going to send this to the blockchain. Okay? And now Bob's going to be the victim because he's owed 1 coin from Alice. What Alice could do is tell a miner, I'm going to increase the fee because I want to get some of my coins back and make sure Bob doesn't get it. And the point is that Bob is always losing money every time he increases the fee, but Alice has already lost that money, so she's strictly just getting money back until she burns everything. Is that sort of the idea?
Are you referring to collusion with miners or?
More for the reason that the miner will always take the transaction of the hash fee. So the idea is that Bob wants to pay the minimal fee because that's his money, and Alice is willing to pay a high fee because Alice was never going to get the money back anyway. So she's burning the money until the miner gives her the transaction.
Okay, so the way to construct this chain of mad HTLCs is to use the same secret as in regular HTLCs. That would be in hash lock 1.
Yep.
But for the second part, for the second hash lock, every backman.
I just mean for the attack. I'm just trying to clarify the attack in my mind, not the solution.
Oh, sorry.
I think. Can I take this, Itay?
Sure.
Yeah. Sorry, I have camera issues, so just voice. But
No worries.
I think what Pat is saying that Alice could counter bribe, and the thing is that this is something interesting to analyze, but it is not clear when this will end. You need to make assumptions on the timing. And
I guess my main point is that maybe I've mixed up the roles. So Alice is sending coins to Bob. So Alice, in the honest case, should always give the coins to Bob. Now Alice is trying to get her coins back. Maybe Dave has been paid, and Alice wants to get her coins back. So then Bob has an incentive, to pay the lowest fee because he's owed 1 coin from Alice.
Yeah.
But Alice is willing to pay any fee she wants because, she's trying to get her coins back, and she wasn't going to get.
Yeah, and that's an interesting question, and the answer really depends on the latency and how confident they are, because the last one to put in the highest fee when the new block is created is going to get that transaction. So it becomes sort of a race.
Yeah.
And the result really depends on latencies and things that you don't really want your security to rely upon. So you could analyze this, or you could just go ahead and use meta HTLC, and then you don't need to start gambling.
Yeah. And moreover, when you get this race, the stopping condition would be that you just depleted all the tokens, right? You'd pay 99% of the tokens as fee, and then you'd get a mere 1%. And that means you'd have to pay something in the order of the as fee what's held in the contract, and that's undesirable.
Yeah, completely undesirable. Okay, I think I got an idea then. I just want to clarify that. There's also some questions. So this one's by Daoban. He says, would you say the problem with HTLCs depends on Siebel resistance methods used by the underlying chain. In other words, could you argue that HTLCs are a safe mechanism in a proof of authority network? I'm trying to think what he means by that. Do you mean like,
No.
is it because you're interacting with unknown nodes that this is a problem?
No, this really does. It really doesn't matter what the consensus mechanism is.
Mhm.
As long as the miners add transactions because of incentives, the problem exists. So the consensus mechanisms for forming the chain doesn't matter.
Okay. And then there's one more question, again by Dilban. What other attacks besides bribery are HTLCs susceptible to?
So I'm not familiar with, when we talk about attacking HTLC is because we're accustomed to this premise that says that if the transaction was posted before the timeout, then it's supposed to get in. And I think this is the main attack vector of stalling that transaction and not letting it get inside. I'm not familiar with attacks on the hash itself. So maybe Itay, you want to add something or?
No.
I can think of one attack. I think this was like the one by, maybe it was Aviv Zahar or someone else. What you could do is if these channels have short timeouts, you could set up thousands of routes such that, you know, if there was, you could set up, let's say 1,000 routes and every route is 13 in length, you know, maximum path. And then if you do one big dispute with all your channels at once, then there's just not enough block capacity to get all the HTLCs into the blockchain. But that relies on short timeouts.
Is that Aviv Zar's paper?
I think so. I think that was one of the papers. I forget the name of it. I just remember the technique.
I think, yeah, okay.
There was another one around the idea of the justice transaction. But that was mostly like a quirk in how the transactions were formatted. Alice can't bump the fee, but Bob can. So it was a bit awkward. Okay, is there any other questions, by the way, in the audience? We have, I guess if there's no more questions, we can have a 5-minute break until Julia, joins and gives her talk.
Just briefly, Patty, regarding the paper from Zohar's group, it's a really cool attack with these loops that they form, and I think that Mad HTLC is going to resolve that because the point becomes the miners being able to prioritize transactions off the mempool.
Yep.
So the attack is valid against the existing mechanism, but if you replace the HTLC with Mad HTLC, you become secure.
Okay. I have one question actually. Do you guys prefer there's two ways to do this routing. There's one with HTLCs, and the other one is like micropayments, where you send rapid payments through the route and you don't do any HTLCs. And the idea is that if it doesn't come back, you lose a penny. Like the interledger approach. Do you guys have a preference for either one or comments on either one? So once HTLC was a strictly, value comes in and value comes back. The other ones is like rapid micropayments, and you'll do like 10,000 payments sequentially to get the volume through.
Yeah, that's a good point. So this affects though only the multi-hop case.
Mm-hmm.
And the chain itself, the single hop still relies on Meta HTLC for disputes in case of misbehavior from one of the sides.
Yeah, no, I'm just wondering, so with the interledger approach, the idea is that there's never any disputes because it's too expensive to do on chain. I mean, the idea is that if there's like 3 hops from Alice to Div, we just keep sending a penny through. So every route is a penny. So if one penny doesn't get through, you just stop.
But across a single chain, the pennies accrue to a large amount.
Yeah, over time, yeah.
One of the sides could choose to settle at historic deprecated states that is more convenient for her. Mm-hmm. And then you use again HTLC just for that single channel. And that's susceptible, that's vulnerable to the attack.
Okay.
May I ask a question?
Yeah, go for it.
Yeah. Hi, Ito. It was a great talk. So basically, I have a question about the scenario 3. Can you go back to that slide? Scenario 3. So you said that both Ant-Man. So basically, Ant-Man is Alice and Batman, I would view it as Bob. So
Yeah.
in this scenario, I think Ant-Man is honest, and if Ant-Man is honest and Batman is malicious, and miners can reveal the pre-image of HTLC 1 and HTLC 2, and then claim the money in the deposit contract, right? Or the money locked in the deposit.
And the
so
collateral.
yeah, and also the collateral. So does that mean if Batman got punished just because he's interacting with a malicious admin?
The other way around, but yes. But please know that by being malicious, Batman actually loses additional tokens. He loses the collateral tokens.
Yes, but that is from the Batman viewpoint. But from the Ant-Man's viewpoint, it seems like, okay, now I try to be honest and try to exchange something with Batman, and Batman tried to claim something from. So yeah, it shows the pre-image. No. Batman is the later one. Okay, so after the time block, yeah.
Yes. So yes, Ant-Man does lose in this scenario, and I'll say that it can be avoided, or it can become super costly for Batman to do stuff like that.
Mm-hmm.
And the way to do that is by increasing the amount of tokens in the collateral, but that requires more collaterals, more tokens as a deposit.
Yeah, as the deposit. Yeah,
that
right.
creates an additional overhead that Batman has to have these tokens initially and deposit them in this collateral. So theoretically, you can require a 10-to-1 ratio between these two. And that somehow protects Ant-Man, because then Batman loses 10 times more than what Ant-Man loses.
Okay, I see. But if Batman is honest, and then Ant-Man is actually interacting with an honest person, then he won't get punished, right? So basically, I'm just feel a little bit weird, because from the perspective of the Ant-Man, he get punished just because he's interacting with another malicious malicious person. But if he interacts with another honest person, then if everything goes fine in the scenario 1 or 2, actually he won't get punished, and the money locked in the deposit and collateral won't be claimed by the miners. Am I understood it wrong?
No, you got it perfectly right.
Okay.
This is the deterrence mechanism. Okay, so
yeah.
The way to deter attacks is by threatening the parties that if they misbehave, they're going to lose their money.
I see. Okay, thank you.